So in this video, we're going to take that generalized first order filter a little further and say, let's consider what happens if we put the capacitor in our feedback network. So as we can see, our input network, which previously was labeled as just Zi, only has resistor Ri, and our feedback network now has a resistor Rf and a capacitor Cf. Other than that, we have the same configuration that we saw in the previous video with our general system. So to relate it to that previous circuit, we can say Zi is just Ri, and our Zf, as we had in the previous system, is going to be the parallel combination of Rf and the impedance of C sub f, which is going to be, well, let me write it out explicitly. So C sub f, which is going to be R sub f in parallel with 1 over S times C sub f. So we can find that, again, just by doing that simple equation of the product divided by the sum. So we have R divided by S C sub f, and this is R sub f up here, divided by the sum of the two, so R sub f plus 1 divided by S C sub f. And in the denominator, what we can do then is we can find a common denominator within that denominator to add those two terms. And doing so, our numerator we're leaving unchanged, Rf divided by S Cf, and then finding a common denominator of S Cf in the denominator, we get S Cf Rf plus 1. And so as we've seen in a previous video with similar analysis, these two will cancel out, and we're just going to be left with Rf divided by SCF Rf plus 1. Okay, so we've already considered the generalized form, and we said we know the gain is just going to be our feedback impedance divided by our input impedance. So H of j omega is equal to negative Zf divided by Zi, and so that's because this is an inverting configuration. So we've already analyzed that when we talked about op amps, but of course we could do a similar analysis again. And plugging in our values then for Zf and Zi, what we have is we have negative Rf divided by Ri times this fraction, which is 1 divided by 1 plus j omega Cf Rf. So this would be our transfer function here. So a couple observations that we can make. So we have a couple options. We can compare this to sort of our previous analysis, and we can say by inspection it looks similar to what we've seen before, or we could think through it from the start again in terms of considering our extreme cases. To line up with what is in the notes, let's just say, comparing to what we had before, we can say this has the form of a low-pass filter. So a low-pass filter, and we saw this previously in the notes on Canvas. If you look on page 5-2, this is what we saw for the previous low-pass filter that we considered. It wouldn't be too difficult to go back to sort of our extreme cases method. We say omega equals 0. We're considering this omega here. We see that makes the transfer function 1. Omega equals infinity makes our transfer function 0. So either way works. Our low frequency gain, so this is new, so remember we can have a gain now. So we specify this as being our low frequency gain. It is going to be equal to negative Rf divided by Ri. And so basically that is occurring when our omega is really small, so that this term highlighted is approximately 1. So our gain then is this part here, which is negative Rf divided by I. So far we've said this is a low pass filter, and we said we have a low frequency gain of negative Rf over Ri. And so of course by adjusting Rf and Ri, we can make this value greater than 1. The other sort of important piece of information is our corner frequency, or our 3 dB frequency, or our roll-off frequency. We have several different names for it, omega c. And so we could go through this definition again of this is where our transfer function magnitude is equal to 1 over root 2, or comparing it to our previous equation by inspection, we can say that our corner frequency is 1 over RF times CF. So there's sort of our three key pieces of information from analyzing this active circuit. And of course, the main difference we see here is now we can have some gain to our signal in addition to selectively filtering. Without even writing any of this transfer function, doing any of this math, we could have been able to determine this just from sort of analyzing, or not analyzing, but qualitatively thinking about what's going on with this capacitor impedance as frequencies change. So remember, our capacitor impedance is negative J over omega C. And so what that means is if we have zero frequency, we know for zero frequencies, our capacitor is essentially acting like an open circuit. And for very high frequencies, our capacitor is actually going to be acting like a short circuit. So our impedance is going to be roughly zero. And so what we can see then is for low frequencies, with the capacitor being an open circuit, what that means is we essentially can ignore this capacitor and then we just have our inverting configuration. So for low frequencies, then we just have the inverting configuration and we get this low frequency gain of negative RF over RI. However, if we get to high frequencies, this capacitor can then be approximated as a short circuit. So we have something that looks like this, where we just have a short, and now we essentially ignore this RF because it's in parallel with the short, so the short dominates. So if we go back to our basic equation of our feedback impedance divided by our input impedance, so this right here, we see that now that feedback impedance is zero, so we just have a gain of zero. So the reason I bring that up is you don't necessarily need to do a detailed analysis every time. Sometimes you can just sort of qualitatively think about what certain components are doing at our extremes of frequency in order to figure out what type of filter we have.